This video is about Module 3, Topic 1, Lesson 5. And we're talking about applications of similar triangles. Okay, we are using similar triangles to measure the heights of flagpoles or the widths of rivers using similar triangles. Now, to start off, I want to focus on, and on page 507, I want to focus on this problem right here. Okay, I think we've done problems like 1 and 2 enough that you could write a proportion and solve it. But number 3 is a little bit different. Okay, so I want to find this length right here. Now, first thing to realize with number 3 is that we have two triangles. Okay, I have this smaller triangle, this red triangle here, and I also have a larger, what I'm calling the blue triangle. Okay, and I want to use those two triangles to find the length of x. Okay, the first thing to look at is, are these two triangles, the red triangle and the blue triangle, are they similar? Okay, well, your first instinct may be, well, I have some lengths of angles, maybe it's by side, angle, side. Okay, and that sounds really good, except you don't know the length of x, so you can't do side, angle, side over here. That falls apart because you don't know the length of x. Okay, so it can't be using sides, we only have angles. Well, I have two right angles, okay, and I have this angle right here. That's the same in both triangles. Okay, so the triangles are similar by angle, angle. And because they're similar, I can now write a proportion with some equal ratios. Okay, now I want to do a very common mistake. So don't write this down. This is not correct. Okay, so you could say 4 over 5 is equal to x over 3. Okay, that is incorrect. That's not right. Okay, I'd recommend you pause the video and discuss with those around you what is wrong with that proportion. What about it is incorrect? Go ahead and pause the video. Okay, the thing that's wrong is that 4 and 5 are both whole lengths in the red triangle. It's the kind of the height over the width of the red triangle, and that's fine. Okay. In the blue triangle, the whole height is x. That's also fine. The problem is that 3 is not the full width of the blue triangle. It's only part of it, okay? So instead of using 3, we need to use 8. Okay? That is a correct proportion. You can write this one down, okay? And the way you solve proportions is by cross multiplying. 5 times x is 5x. 8 times 4 is 32. Okay, so we're saying a proportion. We then solve. Let's divide by 5, and x is equal to 6.4. If I had units, I would include them, but I don't have units. Okay, so that's a different kind of problem because we have these nested triangles that will come up in this section as well. Okay, so let's look at some common application. Okay, I'm going to the next page. This is page 509. Okay, and there's some physics. Okay, so if you have a mirror and light will bounce off that mirror, that's probably a thing that you already know. Okay, one thing you should know is the angle of incidence, this angle that it comes in at, perpendicular to the surface of the mirror, it's going to bounce off at the exact same angle. Okay, or maybe for our purposes, we can think about this angle and this angle being the exact same. As it comes in, it'll bounce and bounce off as well. Okay, it's also true if you throw a ball against a wall, it will be like this, except gravity will pull on it. But anyway, if there's no gravity, it would bounce off at the same angle it comes in at. Okay, that's the idea of light. Okay, so we will use that fact of light bouncing with congruent angles to find some missing lengths. Okay, so an example of that is right here. So there's a guy in a green sweater. He puts a mirror on the ground. Okay, and then backs up until he can see the top of the flagpole in the mirror. Okay, so what's happening is from his eyes, not top of his head, from his eyes to the mirror to the top of the flagpole. Okay, now we just learned that as it bounces off the mirror, this angle right here will be the exact same as the angle here. So those angles are the exact same. Okay, and we measure heights perpendicular to the ground. Okay, so this is perpendicular to the ground. Okay, and we have similar triangles by the angle-angle similarity criteria. Okay, and in fact, all of these will use the angle-angle similarity criteria. Okay, now let's give you an example where you have lengths. Okay, so let me erase this. A very similar problem down here. Okay, Maureen goes to the park and uses the mirror method. So there's a mirror down here to gather enough information to calculate the height of one of the trees. Okay, it's a common thing people do in parks. They wonder how tall trees are. I'm just kidding. But for some reason, she wants to know how tall the tree is. The figure shows her measurements. So her eyes, now it's a little bit incorrect. It really should be to her eyes, not the top of her head. But let's say her eyes are 5.5 feet off the ground. And she is standing 4 feet away from the mirror. And that mirror is 16 feet away from the tree. Okay, so let's see here. Are the triangles similar? Well, we have right angles. Again, you measure height perpendicular to the ground. We also have the angle of incidence, same as the angle of reflection. Okay, so those angles are similar, and these are similar by angle-angle. Okay, and this is the height of the tree right here. Okay, so I can write down a proportion. Now, there's different kinds of proportions you could write. Okay, and I don't really care which proportion you write. Okay, you can do a corresponding ratio where, let's say, x corresponds with 5.5. Okay, and that's equal to, now I did tree over Maureen equals tree over Maureen, so it'd be 16 over 4. That's fine. Those are corresponding ratios. Okay, we could also look at a ratio of, let's say, 5.5 over 4. So this is a kind of a height to distance. Get that lined up better. A height to distance ratio. Okay, within each triangle. That would be equal to the height to distance for the tree, x over 16. This is a within figure ratio. Okay, in truth, it doesn't matter which kind of ratio you do. This, I'm correspondence, x over 5.5 equals 16 over 4, or 5.5 over 4 equals x over 16. Either one is fine. You'll notice that if you cross multiply x times 4 or x times 4, you get 4x. And if you do 16 times 5.5 or 16 times 5.5, you get 88. Okay, again, it doesn't matter what kind of ratio. You still get the same equation down here. You then divide by 4, and you find that x is 22 feet. Make sure you have units for these problems, as it's an application problem, so you should give units. Okay? All right, down here, number 2, Stacy wants to try the mirror method to measure the height of one of her trees. She calculates that the distance between her and the mirror on the ground is 3 feet. And the distance between the mirror and the tree is 18 feet. Stacy's height is 60 inches. Draw a diagram of this situation, then calculate the height of this tree. Okay, now I want to push you and see if you can draw a diagram, even if it's two triangles is fine, but draw a diagram of Stacy and the mirror, okay, and the tree. Draw on the similar triangles and label it and get that far. Okay, so please pause the video and draw a diagram that models this situation. You can pause the video. Okay, here's Stacy. There's Stacy, okay, and then there's the ground, okay, and I'll just put the mirror here, and from her eyes to the mirror, top of the tree, and so here's my tree. Okay, all right. So I need some distances here. Okay, measure perpendicular. Okay, so the first thing given is 3 feet, which is the distance between her, meaning on the ground, and the mirror, which is 3 feet. Okay, and then between the mirror and the tree, this is 18 feet. Okay, and then her eye height to her eye is 60 inches. Now, everything else is in feet, 3 feet, 18 feet. I'm going to do this one as well in feet. So 60 inches divided by 12 inches is 5 feet. So I'm going to write 5 feet here. Her eyes are 5 feet off the ground. Okay, and I want to find the height of the tree. That's the diagram you should have. Okay, now I want you to pause the video and try to find with this diagram the height of the tree. Okay, write a proportion. I don't care if it's corresponding ratios or within figure ratios. Write a proportion and solve it. You can pause the video. Okay, so I'm going to use I guess it doesn't matter which ratio you use. I'm going to do 5/3. Okay, this within figure ratio is equal to x over 18. Okay, but no matter what ratio you write, after you cross multiply, you should get 3x equals 5 times 18, which is 90. Okay, then if you divide by 3 to both sides, you find that x is 30 feet. Okay, again, make sure you have units as it's a word problem. Okay. Okay, in the next problem, we are not using a mirror. So let's say Stacy gets to the park and she wants to know the height of the tree. Again, that's would be a very normal thing to do in this world. Stacy notices that another tree casts a shadow and suggests using shadows to calculate the tree's height, okay, which is another thing you can do, okay. She lines herself up with the tree's shadow so that the tip of her shadow, so let me just sketch a picture here. So here I have Stacy's shadow on the ground, okay, and where the shadow ends, the top of her head in the shadow, okay, it matches up with the tree's shadow. The tree's down here, and the top of that tree shadow hits the exact same point. Okay, so she moves around and finds out so that her shadow and the tip of the tree's shadow meet. Okay, she then measures the distance from herself to the tip of the shadow. That's 6 feet. Okay, and then measures the distance from herself to the tree is 15 feet, and she knows that she is about 5.5 feet tall. Okay, we want to find the height of the tree. Okay, I would encourage you to pause the video and try to find the height of the tree, and the hint that I will give you is the tree is taller than 15 feet. Okay, so if you didn't answer that's less than 15 feet, you've done something wrong. Okay, go ahead and pause the video and try to find the height of the tree. You can pause the video. Okay, so last time I did a within figure ratio. This time I will do a corresponding ratio. Okay, x corresponds, this height corresponds to Stacy's height of 5.5. Okay, the next one, and here's where the trick is, okay, is that I want to use the whole length of the shadow. Okay, I'm not using 15. I know it's tempting to use 15. It's a large number. It feels about like the right length. Okay, it's actually not 15. This length is 21 feet. Okay, so 21 over, that's the height of the shadow, to Stacy's shadow is 6 feet. Okay, again, the most common mistake, that's what I brought up at the very, very beginning of this video, was that this length is often wrong. You want to use the 15, it's not 15. Okay, so now that we have a proportion, let's solve it. So x times 6 is 6x, and 21 times 5.5 is 115.5. Okay, and then to solve this, I'm going to divide both sides by 6, and x is 19.25, 5 feet. Okay, that's the height of the tree using shadows. Okay, I hope you get that idea. Okay, oh, one thing we didn't do with this problem, we should have done, is to talk about why the triangles are similar. Okay, now we measure height perpendicular to the ground. Okay, the other thing that's the exact same is at the same time of day, this angle that the sun makes is the same for everything at the same time, right? So it's true that she doesn't have to line up with the tip of the shadow of the tree. Okay, she could be anywhere and measure her height and her shadow length, and then measure the tree's shadow length and find the height of it, because at the same moment of each time, the shadow lengths, will create the same angles, because the sun's anyway the same height for everybody at the same time. All right, so let's move on. I think we get that idea. We can do the volleyball problem, but I think we get this idea. So let's move on to determining width indirectly. Okay, when it's not reasonable for you to measure the width of something in the real world directly, you can use indirect measurement. So let's say a group of friends visit a park, and they want to figure out how wide the creek is. Again, just as normal as wanting to know the height of trees, I guess. You know how wide the creek is. Lauren stands 5 feet from one side of the creek, and Caleb stands 5 feet from the other side of the creek, directly across. So here's Lauren's starting point and Caleb's starting point. Okay, and they're both 5 feet from the water of the creek. Okay, then each friend walk away from each other in opposite parallel directions. Okay, so Caleb walks 50 feet and Lauren walks 12 feet. Okay, and they walk until they line up directly so that their line of sight and where it crosses the original position hits directly where that shore line hits. Now, how they would know that, I have no idea, but whatever, it's a math problem. Okay, now, if these are parallel, then what we get is alternate interior angles. Okay, and if you're thinking, Mr. Lewis, we don't even need that because we have vertical angles, you're right. Okay, we also have vertical angles here. So these are definitely similar by angle, and we have angle, angle, angle. Okay, how do we know the triangles are similar? Well, by the angle, angle similarity criteria. Okay, now before I tackle the width of the creek, I'm first going to find this whole length right here. Okay, I'm going to call this length x. Okay, it includes the 5 feet on Caleb's side, but it's that full length. Okay, and I'm going to write a proportion that is x over 50. That's a kind of a distance across the creek, and then a walking distance, and that's for Caleb. And for Lauren, her distance to the creek is 5 feet, and her walking distance is 12 feet. Okay, get that? That's the right correspondence for these similar triangles. If I cross multiply x times 12 is 12x. And 5 times 50 is 250. And then to divide both sides by 12, and x is equal to 20.83 repeating. Okay, now that is the total length from the shore on Lauren's side to where Caleb started. It is not the width of the creek, okay, because we haven't taken into account this 5 feet right here. So if I subtract the 5 feet, then I get 15.83 repeating feet, and that is the width of the creek. Okay, so it's kind of a weird problem, but we can figure out some more complicated situations of figuring out width indirectly. Okay, let's do a few more of those. Okay, there's also a ravine, a deep hollow in the earth, okay, on another edge of the park. Rachel and Gavin take measurements to calculate the width of the ravine indirectly. The figure shows their measurements. Calculate the width of the ravine. Okay, now this one's a lot like the previous one with Caleb and Lauren. So I'm going to ask you to pause the video and try to figure out with the information in this diagram what is the width of the ravine. You can pause the video. Okay, the first thing to do is to make sure that these triangles are similar. Okay, again, if the triangles are not similar, we can't write a proportion, we can't solve it. Okay, so I have right angles, and that's super important we have these right angles, very small right angles. Okay, we also have the vertical angles, and that's enough for us. Okay, that's enough for us. With the vertical angles and right angles, they're similar by angle. Okay, and like we did last time, I'm going to find this length right here from Rachel's side all the way to Gavin's starting position. Okay, I'm going to call that x. And I know that, let's see here, I'm just going to use corresponding ratios this time just to switch it up to kind of keep you flexible. Okay, so x is the kind of the ravine length on Gavin's side divided by that similar distance on Rachel's side, which is 6. Those correspond to each other. Okay, and then the length that Gavin walked is 60 divided by the length Rachel walked, which is 15. Okay, these correspond to each other. They're corresponding ratios. Okay, again, x over 6 equals 60 over 15. Those match each other. Okay, so to cross multiply, x times 15 is 15x. And 6 times 60 is 360. Okay. And now to solve the equation, we would divide both sides by 15. And x equals 24. But that's the full length. I've not taken into account this 8 feet that Gavin stood away from the edge of the ravine. And so I'm now going to subtract off that 8 feet. I'm left with 16 feet. That ravine is 16 feet wide. Let's do one more like this. There's a large pond in the park, and Elijah wants to calculate the distance across the widest part of the pond. I'm not sure what kind of park these people are at. They want to measure lengths of stuff, but I don't know. Labeled as DE. So I want to know how long this is, X. Okay. To indirectly calculate this distance, he first placed a stake at point A. From point A, he could see the pond's edge on both sides. At point D and E, where he also put stakes. We put stakes at A, D, and E. These are the stakes right here. This right there are the stakes. Okay. At a narrow point of the pond, he placed stakes at points B and C along the string so that BC is parallel to DE. Then he measured the distance from point A to point D and from point A to B. So we have this diagram and the lengths that are drawn there. Okay, calculate the distance across the widest part of the pond. Please pause the video and figure out why these two triangles are similar. I don't have right triangles anymore, but I do have two triangles, and I have angle A in both of them, okay? And I don't have another angle or another length until I remember that we have it parallel, okay? So that BC is parallel to DE, and if they're parallel, then I have corresponding angles right here and right here. Two arcs, so it's different, okay? So with the corresponding angles, they must be similar by the angle-angle similarity criteria. Okay, again, we're using angle-angle exclusively in this lesson because you don't have enough lengths to use any lengths. Okay, so let's use, I think I used corresponding last time, so I'll use a within figure ratio this time. And so I want to know, let's say 16 over 20 is a left to bottom ratio. Okay, it's a left to bottom ratio. Okay, so with the big triangle ADE, the left is 35 and that bottom is x. Okay, left to bottom ratio. And if I cross multiply, 16 times x is 16x, and 20 times 35 is 700. And then you can divide both sides by 16. And you find that x is 43.75 feet. All right, this video is about using similar triangles to find heights or widths. Thank you so much for watching.